Okay, with great pleasure I introduce to you the keynote speakers of EuroVis 2017, Fernanda, Viegas and Wattenberg. For 15, for 20 years I am a big fan of their work. They represent everything I think is important and exciting in our field. They excel in all those aspects, and I'll try to explain a bit on that. I think three keywords are important here. There's science, there's art, there's impact. Concerning the science, well, Martin has a PhD in mathematics from Berkeley. Fernanda has a PhD from MIT Media Lab. They published a lot of papers in IEEE, EuroVis, Viegas, and Kai, etc. They're heavily cited, so they're really part of our academic community, and they have brought many contributions to that. Okay, that's great. But what makes them really amazing are the next aspects, the art and the impact. Concerning the art, when you look them up at the website, Martin describes himself as a computer scientist and an artist. Fernanda tells you she's a computational designer. Okay. The work is a delight to look at. It's always very clean, polished, beautiful, nice to interact with, totally awesome, clean, wonderful. Okay, you may think that's the art part, but it goes much deeper than that. The real art of their work is that they attack new issues, new problems. They present them in a way that really makes you think and wonder and doubt and ask questions yourself, what's going on. The diversity of the topics they address is close to bizarre. It's about the wind over America, it's about how people cooperate in Wikipedia, how news spreads over the world. You really should look at their websites and scan all those amazing things they've done. And that the art part is accepted very broadly, and as proof of that, the work is accepted, for instance, at the New York Museum of Modern Art, and also at the Whitney Museum, and they regularly have exhibits. Now, concerning impact, their work is used literally by millions of people. Yeah? I think an absolute highlight in our field was the map of the market, developed by Martin in 1999 when he was working at Smart Money. Up to this very day, it's close to, maybe it's just the best example of how the things we develop and use in our community can also have a real impact for real outside audiences to be applied at a big scale. Another example, each time that I give a talk for some audience to tell them what visualization is about, I will always sneak in a little demo of the baby named Voyager. Very clean, very playful, and shows how visualization can help you to explore a topic that's very familiar to all of you. In about 2005, 2006, Fernanda and Martin worked together at IBM. There they launched Many Eyes. Many Eyes was totally revolutionary. It enabled people to upload their data, to visualize it and to discuss it, having a real social dimension to our visualization field, and still a very important concept. After they left IBM, they started a studio, Flow Media, and in 2010 they joined Google. For some years I met Martin and Fernanda, asked what are you doing at Google? Secret stuff we can't tell. So I'm happy that they open up today on the wonderful work they're doing. And again, it's amazing. They really work on what's maybe one of the biggest challenges in our community, not only in our community, but much broader than that. Reading a lot of scary books and articles that AI and deep learning are taking over the world and doing amazing things, and also doing some doubtful and weird things. So It's important for our community to pick this up and try to open up those black boxes and try to understand what's going on here. And do we have to worry about it, or can we check what's going on? In their keynote, I hope they will tell all of us a lot more to it, and I look forward to it very much. And on that,
Thank you, Jack, so much, so much for that amazing introduction. It's a big honor to be here to give one of the keynotes to the EuroVis community. And so what we thought we would do today is to focus on machine learning. It is the most recent work we've been doing. It is very different. It's a very different kind of work. So what we thought we would do today is we put our minds together and we started thinking, what are the, sort of broadly speaking, what are the classes of visualization that we think are really important in machine learning? And very quickly we came up with a few ideas. And so you will see us try to cover a lot of space, a broad landscape. And it's so broad, and visualization can do so much for machine learning, that literally up to this morning, Martin and I were like, oh, but what about this thing? We can't put everything in the talk. Anyway, so you're going to get some of this landscape, there's more, but the things we're going to cover today are some of the things we think are perhaps most important, and perhaps some of the biggest contributions that we can have. This is definitely not work that we do by ourselves. This is work that we do with our team in Cambridge, and some of us in Mountain View. It's really interesting to see the makeup of the group evolving over time. So we're very excited because for the first time in our lives, we're able to hire a visual designer to help us do the work. We also have a couple of machine learning scientists, researchers in our group who are helping.
All right, so we're going to start out by talking a little bit about artificial intelligence as it used to be. And I want to have a quick demo here. So speaking of art, this is an artwork that I created quite a while ago that illustrates sort of old style AI. This is a thing you can play with this on the web. It's open right now. And the idea is that you play against the machine, you play chess, and as you play, you can see every move that it's thinking about. And it's interesting for a bunch of reasons, I think. One is it's just fun to play chess. Another is it actually becomes almost like a visualization of machine stupidity. It's just trying all sorts of things at once, you know, thousands and thousands and thousands of moves. And in the end, it doesn't even play a very good game, but it is sort of fun to watch it mess up. So that's old style visualization, or old style machine learning, or old style AI. What is the new style? What is the intelligence? Well, let's contrast it. So the old style, this is actually literally a tiny piece of code from that chess game. And it's all written as rules. It's very, very explicit. It's calculating values, probably not even particularly good rules, but at least you can understand them. Like if you look at this, you're seeing words that you can recognize. And you have some sense that it's just sitting there looking at a bunch of moves and operating according to rules that a human wrote down, a human understood, or at least once understood when he first wrote the code. What about AI today? So today, probably the big news is neural networks, deep learning. Now these are things that have been around for many, many years, since the middle of the 20th century. And a neural net is a system that it's inspired by the human brain. They're not like real neurons there, and it is not meant to tell you something One of the key things about neural nets is they're trained on data. There's no rule written down to explain how it does something, but it just learns some kind of accretion, seeing many, many examples. And perhaps most important in the very short term is that they're getting really impressive practical results today. Neural networks were something that I think had great intellectual interest for a lot of people for decades, but only when they actually started beating state-of-the-art algorithms done by other means did they really start to take off. So now we're faced with a situation where machine learning is becoming more and more of a force in the technology world, and we really start to want to think about it carefully. It is very different from traditional software, things with traditional rules. And again, the key thing is that computers with machine learning learn from the world. We don't write the rules, that's a benefit, but the challenge is we don't always know what the computer is doing. And perhaps more importantly, we may not be able to control them if we don't know what they're doing. In fact, we're seeing a whole lot of press. I think graphic designers are very happy to have something other than a glowing green brain to draw, so now they draw black boxes. But we see press and sort of describing this in various ways, that this issue of what are these things doing? They're doing it very well, but what is it? And so this is where we say that visualization can help. And so, as Fernanda said, in this talk we'd like to give you a broad overview of some of the ways visualization can sort of help us understand machine learning. And one thing I want to emphasize is that not all of the work we're going to show here is our own work. We really want to give you a sense of some of the key things happening in the field, because we think this is an incredibly exciting area for the visualization community overall.
So we're going to start with the notion of education and the right manipulation. And there are three things here that we wanted to highlight. One is to use visualization to show how ML systems themselves work. Since they are quite complicated, they can be massive, and they're doing weird things that we're not used to. The second is, how do you start explaining some of the algorithms? And here, I feel like we really, as a community, have an interesting contribution to make in terms of direct manipulation. We're really good at putting things out that people want to interact with, right? So are there little simulations? Are there things that we can bring to the forefront to start giving people an intuition of how these systems work? And then finally, the third thing is when machine learning meets real life. So one of the most important aspects of machine learning is that it's starting to be ubiquitous in how decisions get made every day. So it's not just some computer science theory or algorithm running its background. Things are starting to decide who gets a loan, who gets a job, right? And so these are really important decisions that we really believe, and we'll give you an example of where visualization can play a really interesting role. So to start with, we're going to talk about education from the perspective of trying to show what a very, very simple network does. And we used visualization to show what each neuron does in the network. So let me very quickly move over here. I want to do this. Okay, so this is a project called TensorFlow Playground. This is public. Not only is it public, it's open source. And basically, again, this is our attempt at visualizing what a toy network might look like. So what we're trying to get the network to do is to figure out this result here on the right. And I'm going to even change the result itself. So, actually, let me see if I can very quickly reload, because I want to, do we have internet connection? Please tell us we have internet connection. I'm going to live dangerously and try to, okay. Let me stop. I'm not going to live dangerously anymore. So imagine I have a very small network. All it's trying to do is separate the blue dots from the orange dots. So a linear separation is fine. And what I'm trying to explain is that whenever we have networks, we have these things called features that we can train with. So this is a feature here. My first feature Simply, all it knows what to do is to divide the space horizontally, okay? My second feature, all it knows to do is to divide the space vertically. That's all it does. And my network is made up of only these two features, and now I'm going to go ahead and train it. So I start training it, and boom, obviously it's a very simple problem. It solves it. You can see what was happening here with my loss function. You can see how it solved the space that I wanted to solve. And now I'm going to give it a little bit of a more complicated data set to play with. So I have now two circles of dots with the blue in the middle and the orange around, concentric circles, okay? I'm going to keep my network as dumb as possible, so all I have are these two features, again. And I'm going to run it, and obviously it can't solve that space. Okay, so I'm going to stop, and I'm going to start doing things to my network. I'm going to add a little hidden layer. And maybe I decide that this hidden layer should have 4 neurons. So this is my hidden layer here. And I have 4 neurons. Okay, so now I'm going to try to train it again and see if this is enough. So I'm going to play, and boom. Okay, I'm doing fine, I'm doing well. And you can see how each one of these neurons, and again, this is how visualization starts to play a role. I highlight each one of the neurons, and it's showing me how each neuron divides the space for itself, okay? Let me pause and just say something. This visualization came out of us internally at Google trying to retrain really good engineers to understand ML systems. Google had these internal courses where basically we're trying to retrain all of our engineers to be able to work with machine learning. They never had anything like this. All they had was command line interfaces. All these little changes that you made take a ton of time in command line world. So we decided internally, can a visualization help? Can we build something that would allow engineers to very quickly get a sense of what machine learning, what these deep learning systems are doing? We built this. This became so important that all the internal introductory courses at Google use this. A ton. So you're going to see how we can do more interesting stuff here. So it was so useful that we decided to open source. So let me keep going here with our favorite example. So this is what is called the Swiss roll. And this is the hardest data set that this little network can solve, or at least can try to solve. So what I'm going to do is I'm going to start adding a bunch of layers. I'm going to add some neurons more.
Raising its IQ.
We're raising its IQ, yes. That's true. I'm going to go for it. Okay. I'm going to train it. Let's see how we do. It's trying really hard, but it's kind of stuck. All right, so I'm going to stop, and I'm now going to do something that real engineers do with real systems, is I'm going to add more features. This is called feature engineering. I'm doing it with clicking here. But basically, this is what you start adding features. You start optimizing. So I'm going to now try again. My network is trying really hard. It's suffering, but hopefully at one point it can. Okay, I'm going to stop. I'm going to stop here. So it didn't do really well, but it got somewhere. Not where I wanted, but you can see the struggle. All right. Let me try one last thing, see if this is salvageable. I'm going to add some noise to my training data. I'm going to retry. Let's see if I do any better this time. Ooh, I think there's some promise here. Look at that. Okay. All right, I'm going to call this a success for now. In a few seconds, this is very successful. But what I just did there, I just added some noise to my training data, okay? Again, the ability of doing these things really quickly in a really immediate UI is extremely rare. And so what happened when we open sourced this, you can play with much more sophisticated, you can play with the learning rate, you can play with a bunch of stuff here. There are a ton of bells and whistles here. But what happened, that was really cool, is we open sourced this and people went nuts on the web trying to solve this Swiss roll thing. The other thing we started seeing is that people, because they were playing with these things, they started understanding some principles of machine learning that actually you would have to go back to textbooks, machine learning textbooks to pick up. So they're like, oh, this is how, adding noise changes everything, or this is how changing the learning rate affects the results. And so this is exactly the kind of intuition that we were trying to augment as we were building this tool. So let me just go back here very quickly. And so the impact has been interesting to see. As I said, internally at Google, this is now widespread. We've only used this thing for introductory courses. It has sped up learning by 10 times internally at Google. These are highly technically skilled people. At GitHub, this went wild with the number of stars and forks that it got. And then just the number of views it gets, unique views. And then finally, the other thing that I was really happy to see is that a bunch of universities are using this to teach machine learning. So again, just having this really easy to use interface that you don't have to change your command line, sit there, recompile everything, see what happened. Huge. We already knew this as a community, right? So we can really, really help here. Oh yeah, so this is like the Reddit community going over and trying to solve the Swiss roll problem. And it's really cool because people started competing against each other. So this, if I'm not mistaken, is one of the winners where they found out that they could have a single layer, a single hidden layer to solve the Swiss roll. So they did much better than I did. And then versus this other example where this person used only 2 features. The only 2 little features that I started with in the beginning, they were able to solve this thing. A different kind of visual explanation that I think is really interesting in our community could contribute a lot. It's just having visual explanations of algorithms, of what prediction looks like or clustering. And so we wrote this article here called How to Use t-SNE Effectively, about some of the caveats, some of the gotchas with this projection technique. And I want to call out attention to this journal called distill.pub. This is a journal where their main idea is to be a visual journal that has really excellent explanations of things. And by explanations, they specifically mean visual, interactive explanations. So the thing we did with t-SNE has a whole sandbox that you can play with these algorithms. You can see some of the things there. This one is a very beautiful one. It's not ours. This one was you start writing something and it visualizes to you the probability of the next letter that it thinks you're going to write. So it's really interesting. Okay, finally, the last thing about education. This is where we start talking about real life decisions being made by algorithms. So last year, an important paper came out that started to define what we mean when we talk about machine learning fairness, and talked about how different definitions of machine learning fairness have different trade-offs, and how you cannot have all of these definitions exist at once. Anyway, it was a highly mathematical, kind of abstract paper that was really important for the community. So Martin and I decided to visualize some of the fairness definitions that the authors were talking about. Things like, oh, do you want to do demographic parity? The scenario was one where a bank was deciding whether or not to give loans to different populations, okay, with different distributions. And whenever you use one of these different fairness we did this small, simple, interactive visualization, put it on the web, and thought, yeah, maybe someone will look at it, maybe they won't. It went viral. And people kept referring back to this, because finally it allowed a lot of people to grasp some of these mathematical definitions, but not only that, the trade-offs, the very real trade-offs that you're making as you're choosing these long applications and some of the algorithms behind them. And so we got pinged, and we got pinged by people, for instance, in the criminal justice system that were like, can I use a visualization like this to decide on some of the criminal cases? How do I do this? So just having the ability of visually explaining some of these things can have a really huge impact.
So you can see there's a lot to be done in terms of human learning as well as machine learning. Let's talk for a little bit about what sort of research questions there are in here. So one thing that we've been thinking about as we go through all of these examples is where would we go with this? Something like the TensorFlow playground that Fernanda showed. It works partly because it's such a tiny net, and it is such a perfect toy example. But it would be fantastic to have something like that with a much more complicated, maybe a real-life data set. How would we do that? As Fernanda mentioned, talking about some of these things, that a lot of this, you want end users to understand what's going on sometimes. Partly because it just affects their lives, partly because it can make their lives more enjoyable to know. How do we do that? What's the right level of complexity? And then finally, thinking about direct manipulation, I think is very important in the machine learning world. We'll talk about that, I think, at least one more time, that this is a community that, for whatever reason, they use matplotlib all the time. They look at these static graphs as part of iPads and Jupyter notebooks. And we, as a community, I think, have a lot to add. Okay, let's talk a little bit about how these systems learn. So one of the key aspects that we keep coming back to is the centrality of data and what these things do. That it's very easy, in fact, a common pitfall for people coming to the field is that they'll become hyper-focused on particular neural network architectures, when in fact, the thing that really matters in the end is the training data. And so we'd like to sort of talk about, how you can sort of sift through that. So, it controls what machine learning does, it's massive. One of the sort of subtler issues is that it's rare that you know what's important in the training data. If you knew exactly which features were relevant, you probably would not be using a neural network in the first place. You'd just use, maybe linear regression on those very important features or something very simple. So almost by definition, you're in a regime where it's a bit mysterious what your data even mean. And finally, there's this interplay. This happens in other fields too, but it can be very acute in machine learning between both the broad statistics matter and outliers being quite critical. So we'll give you an example of an internal tool that we built that helps you kind of explore an image data set. Okay? And I think images are a good example of the kind of thing I just talked about, because the data comes in the form of pixels, and individual pixels, not particularly meaningful. How do you explore it? So let's take a look. So we're looking at a data set of tens of thousands of 32 by 32 images. They're divided into 10 classes, and let's take a look at how we would see a data set like that. Okay, so we start here, and we arrange all of the images in front of you. And we've arranged them in this case in a very simple way by the actual label, the label given in the data set itself. So you can see we have airplanes, we have automobiles, birds, cats, deer. This CFAR10 data set is one of the sort of standard things that people test on. Now, one thing that's actually interesting, if you look at it this way, is it actually becomes clear that even without being able to see these tiny images, there are huge differences that, the colors alone seem to tell you the difference between an airplane and a ship and, say, deer and birds. And in fact, we've had people who have worked with this data set, or experts, look at this and say, oh, maybe the problem's not as hard as I thought. It's an interesting reaction. But let's think about how you'd explore this. So one thing you might do is you might say, well, if color is important, let me be very explicit about that. So one thing we can do is we can sort of arrange and facet, essentially, by these things. And here we've put things according to where the dominant hue is in the picture. And this gives you even more clearly a view of like, okay, ships, airplanes, very blue, these other things more brownish, and so forth. And a few purple things slipping in. Okay, so that's interesting, but you might have been able to see that just by kind of looking at these things yourself. What else can we do? Yeah, maybe we should actually take a look at what these individual things look like. Let's look at some of these orange cats. Let me see. It's kind of fun actually to play with these. Yeah, let's look at some of these planes. You can see there's all sorts of planes. Weird military planes. It's fascinating, right? Okay. So it's a whole smooth thing. What else can we do? All right, let's take a look at a confusion matrix. So now we're incorporating some information from the machine learning system itself. And in this case, we've trained something to recognize these classes. And we can create a matrix like this that divides, so on them, we still have horizontal rows being the same labels of the actual thing. So everything in the airplane row is an airplane, everything in the automobile row is automobile, and so forth. But now vertically, we've created facets that show you what the network thinks it is. So luckily there's this huge fat diagonal here, which indicates it's getting most of the things right. So we can look here and zoom in and we can see, yeah, these are the airplanes that really look like airplanes. Yeah, fair enough. But we can also look at the errors as well. Those are a little bit more interesting. And certainly if you're debugging the network, that becomes a little bit more dramatic. So one thing we can do is let's filter by correctness. And let's take out the correct ones. All right, good. Okay, when we do this, we've now removed all of those correct ones, and we're old, so we can get a slightly better view of the incorrect ones. And let's zoom in, just take a little look. One thing that is fun is, let's look at dogs, for example, that look like cats. It's a little bit maybe embarrassing for those dogs. But you can see they really do look like cats. They're kind of curled up in this kind of comfy position. They look like they're going to start purring any minute. Meanwhile, we can look at other things too. We could say, what about, say, airplanes that look like birds? Yeah, you can sort of see those are a little bit bird-like. We could look at other things too. We could say, well, there are very few airplanes that look like deer. Like, how on earth could that happen? The weird thing is when you look at this, you're like, yeah, I totally see that as a deer. Computer is not so crazy. So you start to learn things. This sort of, by the way, shows you why this is an actual hard task. You're not just deciding that hue, that this is actually very subtle. There's another thing. Let's look at some other things here. Like, what about, say, dogs that it thought were, let's say, frogs, for example. Oops. So those are sort of frog-like. What about, let's say, things that, let's see, we've got some other interesting things in here. What about frogs that look like airplanes? Actually, this frog looks a lot like an airplane. Yeah, this thing can actually be quite enjoyable to sit through. And let's look at one more thing. What about, yeah, so this is, let's look at softmax. So we'll do one more. Okay, and this will give us another view. So this gives us sort of the confidence that it has in various classes. And so here, let's look at things that were labeled as dogs that it was super confident or was highly unconfident about, interested. What about things labeled?
So,
you have it.
Yeah, I was just going to say that the way I read this is the more to the right an image is here, the more confident the network is that that is indeed whatever, an airplane or a dog or a cat, right? So it's really good that most of our classes are heavily weighted towards the right here. That's great. That means we're doing well. The more to the left an image is, the more confident the network is that that image is not what it is supposed to be. So right there and then we can see a couple of classes that are actually problematic, like cats. There's a bunch of cats that the computer is actually really confident are not cats and have been So let's look at frogs, for instance. These are images that the network is really, no, hang on. Test labeled frog. Oh yeah, yes, this is the stuff you already showed, sorry. There's a specific one we're looking for here. Where is that example? A really good example. Is it a dog or bird? The mystery of the network. Now I really want to find this thing. Where was it? One more. I can't believe this is not here. Is it?
This is the drama of a lockdown.
Yeah. I will find it for you afterwards and try to, maybe during Q&A. Okay.
There's one beautiful mislabeled example here that's been tripping on the little tradable system for a long time.
We can find it.
Yeah. Okay. All right. So this gives you an example of one way of looking at training data. But there are other things you can do with training data as well, including giving explanations.
So I'm going to give a quick demo that is actually not ours, but it's incredibly cool. So let me just do this. It's called Quick Draw, and this is a project that was done. Oh, I really hope we have. Do we not have internet connection here? I can, while you're trying to find that out. So Quick Draw was a project done by the Creative Lab folks at Google. And yeah, I think we're totally out of the internet. So imagine, if you will, a visual demo. Here's the thing. Quick Draw is a really cool program that kids were using all over. It matches you against an ML system that asks you to draw something in 20 seconds, okay? So it says, you have 20 seconds to draw an airplane, okay? And you very quickly try to sketch the thing. And as you're sketching, the computer is telling you what it thinks you are sketching. So it will say, oh, I know, it's a church. And you're like, oh, no, airplane. Oh, I know, it's a shoe. And you're like, no, darn it. Eventually, either it gets it correctly and your drawing is good, or you don't pass, or it doesn't pass the test. And you do that a few times. So it's a bunch of drawings, that's all it is. Of very simple things like shoe, church, airplane, whatever. But then the really interesting thing from a visual explanation perspective is that after you're done drawing like 5 of these things, it explains to you what it thought you were drawing after you drew. And this is what some of the explanations look like. So basically, it says, this is the Quick Draw system trying to explain to you how it learned what a skull looks like. And then it just shows you.
Or shoe, or jaw, or penis.
We have our demo.
Yes, that is Quick Draw. Yes. Maybe you can give a demo to everyone. So yes, it keeps talking as you're drawing, basically. But here, what it is, it's trying to tell you, this is how I learned what a skull is like. Basically, it gives you a bunch of examples. Okay, that's fine. But then it goes one step further, and it says, remember when I asked you to draw a knife? So this is the drawing I made. So it's showing me my drawing. And then it says, I also thought your drawing looked like these. And it says, okay, a knife, a canoe, or a seesaw. And it overimposes my sketch over one of the prototypical sketches sketches that it was thinking about as it was trying to guess my sketch. Okay, so this is a really cool way of getting back to the user, to the end user, who's not, by the way, an ML, a machine learning expert, doesn't even know what machine learning is, doesn't even care, but it's saying, this is how I'm learning, this is what I'm thinking as I'm seeing you draw. And it's a really useful, friendly, visual explanation of what's happening in this really complex system, okay? And also, people learn, right? I'm looking at this and I'm thinking, oh, really? My knife looks like a seesaw. Ah, interesting. Or when, you know, I don't get it right, and it says, yeah, remember this one you didn't do so well? This is what I was thinking when you were trying to draw. I thought it looked like a face, I thought it looked like an owl, and I thought it looked like a lantern, okay? And it, again, overimposes my own drawing on top of drawings it has from its database, okay? So, as we think about, as we work with the challenge of transparency, there are very many different levels of transparency we want to be cognizant about. One is sort of expert transparency. What is the data? What is my network doing, right? But others is the end consumer who's trying to understand why am I being offered a prediction or a guess or a recommendation? And these are some of the ways that have been successful in saying, this is why I'm giving you this solution or prediction that I'm giving you right now.
So once again, I think it's very interesting to kind of sum up what are the research problems that come out of this. So one thing is, could we automate sort of tools to look through training data and actually that are tuned to the kinds of problems that machine learning engineers have? And I think this is a huge area. There's a lot of importance there. The other is how to show the sort of the needles, the like mysterious errors. I mean, you actually kind of got a sample example here because we were going to show you an example and then we ourselves couldn't find it in the demo. It's a real problem. There are occasionally little mislabeled things that are very difficult to find, and I think there's a lot of interesting work that can be done in finding those outliers. And then what is the right level of complexity for these end user explanations? This is just this eternal theme that keeps coming up. Okay, so we'd like to show you another section of a different kind of visualization. And this is, what we're about to show, this is not our work, but this is something that we see happening in the field, and it's weird enough and interesting enough and potentially powerful enough that we wanted to talk about it here. And some of this I think you'll see actually some fairly well-known imagery, but we wanted to talk about where it sits in the field and maybe where it could go. So there's this big question that happens when you look at an image recognition network, which is, what is the network seeing? It's funny because even with human or animals, like there's been a lot of research by biologists on trying to figure out what are individual neurons doing, what is the optical system doing. And there's a whole way that people tend to attack this. They'll start out with a network like this. This is sort of a conceptual drawing. They'll imagine that you have information coming in the form of pixels that comes out as a classification, and you can just start to wonder, what is like just an individual neuron? What is that particular neuron doing? Okay. So one thing you can do is you can start to trace things back. So some people, there's a guy at MIT, Antonio Giralba, who's done very beautiful work with something called DrawNet. This is also a live demo you can see on the web, where he'll attribute to particular final neurons. He'll say, okay, this is the piece of the image that was very important to it. It was relying on other neurons, looking at sub-pieces, and that gives you a sense of attention. It still doesn't necessarily tell you what those neurons are doing. So there's this kind of fascinating idea, which is that you make your network dream, in a sense. You try to invent an image that maximally activates a neuron. And so what you do is pick a network. You use some sort of gradient descent or gradient descent to find an image starting with something that will cause that neuron to fire as much as possible. It's like a police sketch artist who's like, oh, does this look right? Does this look right? They're trying different things, and finally the person says, many people have tried this. One of, I think, the most compelling examples comes from Jason Yasinski and collaborators. And I want to sort of show you some of the things you see as you start dreaming at different layers of the network. So the very bottom layer, the first layer that's actually like kind of right off the pixels, you see that maximally activating patterns tend to be very simple optical things. You can pretty much say these are edges, these are corners, and so forth. The second layer is really kind of weird because out of the corner of your eye, these look like things, but they're not really things. They're just sort of pieces of things, you know, blobs of various sorts or funny curves at a certain angle. You might wonder exactly what these are. I don't know. By layer 3, you start to see things that start to look a little bit more like natural images. Like these look like big eyes, but they're very complicated, whatever they are. They're still not recognizable. Let's move up the hierarchy. If we go through layer 4 and layer 6, we actually start to see things that really are recognizable. So by layer 6 are these awful-looking tarantula things. Layer 5 here, yeah. We see things that look a little bit more like a blue eye or something up here. In layer 4, there are things that are almost like pinwheels or spheres. It's like geometric shapes. And we can see we're really sort of making our way up in kind of visual hierarchy. And then finally, in this network, the 8th layer is a layer that actually has neurons that correspond to particular image classes. And here it's really weird. I feel like these are sort of like the things you might see if you just sort of imagine to yourself a rocking chair. They're like dim, evanescent images. They're not very concrete, but you can definitely see them. There are these sort of weird dreamlike teddy bears, rocking chairs, even pirate ships happening here. Okay, interesting. All right, there's another thing you can do with this, and there you do the same trick, is that you can start to understand more about even the data in your system. So this all comes from a set of work collectively known as Deep Dream, done by a set of people at Google. And they would start with, you know, much like Jason Yasinski, but with some variations, they would start with some noise, essentially, to begin with. And they would tell the computer, okay, make this look more like a banana, according to my neural network. They would optimize it, they would use some tricks, like let's try to get something that's relatively smooth or has some spatial coherence. And much like those final Jason Yasinski images, you see that it starts to kind of dream up a bunch of bananas. Okay, that's, again, it's sort of interesting. It seems like maybe some kind of art could be done with this. But how can it be useful? So here's the cool thing. So they tried this with a whole bunch of classes, here are 8 of them at the upper left. And you can see they have that same kind of weird mental imagery feeling if you look at the anemone fish or parachutes and so forth. But then, when they went to dumbbells, can anyone spot the problem in the training data? So the interesting thing about the dumbbell class is that every single dream that it had about a dumbbell also included an arm, which as a human, it's actually hard to realize this is sort of a problem. But going back and looking, you're like, oh, basically it was trained to see dumbbells only with an arm, and interestingly, only doing a particular kind of bicep curl. And that is sort of a problem with the data that you've been too narrow. And looking at this actually tells you something about the data, even independent of the neural network. And I think that's kind of fascinating. And it's an example of how you could take an idea from machine learning and possibly apply it back to situations that had nothing to do with machine learning. Now, there's one final thing they did, which I think is very clever, is they said, we have this machine for dreaming. We've been giving it little pieces of garbage to look at and hoping that it will dream interesting things based on that. What if we don't give it garbage? What if we don't give it static, but give it another picture? What will it see then? They did this experiment, tried a few extra tricks, and that led to this sort of well-known deep dream style, or inceptionism style of art, which spread across the web surprisingly quickly. I think it's well on its way to becoming a cliche in the machine learning age, but it's actually quite interesting. And if you look at what's happening, you know, you can see that it's just like looking at clouds in the sky as a kid and seeing images in them. That people will sort of, if it sees a horizon, it will hallucinate as a pagoda. You can see that it turns leaves into birds and so forth. And then it will create these completely psychedelic things as well. So once again, I think just looking at these kind of generative visualizations, to me when I look at them, they're very new and sort of hard to interpret. I think there's a lot of questions for us as a community. You know, can we think of ways to make these more interpretable and less, you know, psychedelic? What is the equivalent of even labeling axes on these? You know, there must be some way that you can kind of calibrate these, because they're showing us something, but it's still hard to know how important any of it is. can we evaluate? Some really interesting work is already starting to be done on this. There's something called network dissection that's been created by researchers at MIT. And I think most interesting of all, you could ask, could we generalize any of this? Are there ways that we could start dreaming about other data sets? I think there's a lot of meat on this bone, so we wanted to leave you with this.
All right, and the last class of visualizations we're going to talk about today has to do with high-dimensional space, which basically is a lot of what happens when you work with deep learning, is these machines tend to work in very high-dimensional spaces that are not intuitive to humans. So a few ideas there. One is this notion of projections and the fact that projections matter. The second, the importance of having interactivity. Again, something we all know in this community. And then finally, we want to finalize with an example of when one of the visualizations we created was actually used for scientific insight. So the first thing about high-dimensional space in the deep learning world is that as a data visualization community, we're very used to thinking about high dimensionality. However, one specific change here from, I think, the kinds of data sets that we as a community are used to thinking about and what happens in high dimensional space in machine learning is that in machine learning, the dimensions themselves or the coordinates may not have any meaning, or at least not any meaning that we as humans can understand. So it can end up looking like a bunch of garbage to us. It's hard to interpret. So as a small warm-up exercise on high dimensionality, let me take you to this very specific example here. What we're looking at here is a small sample of a data set called MNIST. MNIST is kind of like the hello world of machine learning. All it is a data set of handwritten digits, numbers. That's all it is. And it is one of the most well-curated, everybody uses this data set. Whenever you have a new publication, chances are they're going to look at MNIST. And so if we wanted to cluster these little images of numbers, how might we do that? So we might want to zoom in into one of these images, and then we might want to start counting the pixels, and each pixel we're going to see the color of the pixel. So if I look at a pixel at the top that is completely black, I'm going to give that a value of 0. If I look at a pixel that is completely white, I'm going to give it a value of 1. And if I look at, you get the gist, right? If I look at a gray pixel, I'm going to give it a value between 0 and 1. That's all I'm doing. I'm going pixel by pixel, I'm creating a vector. That's all it is. Okay, so I turned an image into a vector. My vector is 784 dimensions long because I have 784 pixels. All right, I'm going to do this for every single image that I have. And what I end up with are these vectors that sometimes are very similar and sometimes are very different. And I'm going to look at the similarity of these vectors and I'm going to start trying to cluster these vectors. Hopefully, in the off chance that I can tell number 8s apart from number 4s, for instance, okay? So let me show you a live demo here. So we created a tool called the Embedding Projector that is also a open source tool that allows you to look into high dimensional spaces. And what we're looking at here right now rotating is the MNIST data set, and we're looking at a PCA projection of that, okay? And I am showing the actual images of each one of those data points. And you can kind of see that as this thing is rotating, now we're starting to look at the zeros, okay? So you kind of maybe did a good job, kind of clustering. And now we're starting to look at some numbers 6. And now it's confused because there's a bunch of numbers there. but let me start interacting with this. I'm actually going to rotate this, and now I can see a bunch of ones, and it's pretty cool how it clusters the ones all together. And this is just PCA. Okay, so I get the sense of this cloud here. Now, the other thing we did with this tool is we allowed you to use different projections. So PCA is the first one you get for free, but then the other projection we allow you to try is TSNE. And you can run TSNE and see, again, this is MNIST, so I'm going to rotate. And you can see how TSNE does a little bit of a better job of clustering things for me. So this is the cluster of 7s. I'm going to try to get to the cluster of 0s here. And then another trick I can do is I can color these things. I'm going to color by the label. So again, this is a human label thing. And now I have my clusters. And I can see whether or not, it's much easier for me to see whether or not we're doing a good job here. And I can see the places of confusion as well. So here, for instance, I have a number 2 that got very close to number 1s, right? Let me see, here are number 2s, but I have an 8 here. The other thing I can do with this tool is I can say rotate here, I'm going to bring in, I can zoom in, I can zoom out, and I can also kind of like click, I'm going to click on the 6. And what it does for me is it highlights the nearest neighbors. This is usually something that really matters in the dimensional space, right? So I can see here, not only does it highlight on the visualization itself, but it also lists to me, it also tells me the distance from my target. So the good news here for me is that all my nearest neighbors in the specific 6 I chose are number 6s as well. But let me see, what if I do, oh, this is an interesting 9, that doesn't look like anything. Let's see, let me click here. That's a 9, whose nearest neighbors tend to be mostly 0s, okay? And it is humanly labeled as 9. So again, and it shows you how some of the nearest neighbors are way down here. And again, this is some of the stuff that you get with these projections, right? But this, and again, this is one of these things that is really hard to come by in machine learning, which is an interactive way to look at your data and look how the system is resolving all the data that it's ingesting.
Yeah, one thing I noticed about this is how this TSNE projection method actually does a remarkably good job of clustering. We had people also, just as with the previous training data example, look at this and say, yeah, I guess it shows it's not that hard a problem after all. It's very interesting. Of course, it's deceptive because there are these outliers in there. Okay, so let's talk about how you use this projector on some other kinds of data. So one of the very interesting things people do in the machine learning world is they don't just cluster images or assign numbers to images, but they'll do this with words, and they'll do it on very large corpora. It's like all the news or all the books. And it turns out that if you create a model that basically sits there predicting co-occurrences of words, in effect, I'm oversimplifying a little bit, you can assign words to points in a medium high dimensional space, several hundred dimensions, so that similar ones are near each other. And it turns out that in this space, there are all sorts of interesting properties that they enjoy. One really interesting thing that was sort of first published about in 2013 is that frequently there are sort of secret meaningful directions, like individual coordinates in these embedding spaces are not that meaningful. But often there's like a direction that will correspond to like capitalness, where if you look at the difference between a capital city and the country it represents, those vectors are not very different for different countries. That there are these meaningful directions. So let's take a look at one of these kind of mysterious word embeddings in the embedding projector and how you might explore it. So here's a very simple PCA view, about 10,000 words. And you can see it looks sort of like a big Gaussian blob. It has some features you might notice, like it's a little bit pointy, and this is the pointy end over here. And what's interesting actually is if you start mousing over these things, you'll see that most of the things in this point are names. The names are sort of this complete outlier in sort of a linear sense. But you really don't see that much detail. So let's take a look at a T-SNE view of this. Okay. So when I do that, once again, I see something that's kind of a blob. It's a little bit hard to interpret. But unlike the previous PCA view, I do see a bunch of tight clusters. And let me just mouse over some of those, and we can sort of see the kinds of things that get put together in this view. We have a very tight cluster here. Oh, look, I think it's this tech, actually, or math, at least. You know, pi, cosine, and omega, theta, mu. So, okay, that's the math cluster. What about this tight cluster down here? Cello, flute, horn, trumpet, reed. And we can click on these and see what it thinks is near to horn. And we can see that largely it's musical instruments, interestingly. No cars or anything. What about some other type clusters? Here's one, not reproductive. This is biology here, reproductive biology. Here we have seasons. And in fact, seasons are kind of interesting. We can zoom in a little bit and whoop, we can actually see that they're arranged in sort of a particular order. So that makes sense. Okay. What else can you do with these? Let's go back to a very big data set here. So this is PCA, but there's something we can do that's sort of interesting. We can actually create our own axes. So PCA basically is sitting there and saying, okay, how do I project these to account for as much variance as possible? But given this is a set of word embeddings, we actually can do different things than that. We could say, for example, let's pick out two particular words and project on the axis formed by those two words. So let's give some examples. And what I'm going to do is actually go through a couple here, and I'm going to go down to a small neighborhood and project there because it's easier. So I'll give you an example of this. Let's just start out by selecting a neighborhood. I'm going to do politics, and I'm going to isolate these points, and it'll give me PCA of this. So this is, again, PCA based on things that are near to politics. So you can see rotating around here, things like culture, religion, stuff like that. It all seems very normal. But now, I'm going to click on the previously saved state here and project on the good to bad axis. Okay, so now, left to right, left is good, and this is all good according to this particular one. I'm not going to make any at all judgments here. And on the right is bad. And interestingly enough, you can see that sort of the worst neighbor of politics is violence. That seems reasonable. Whereas relations and discussion are on the good side. Much more neutral, I guess, in this view, in unions or social or so forth. What about other neighborhoods? Let's take a look at some of these things you can do. So instead of politics, let's look at some professions. So here, the way I got to this is neighbors and musician. And what I've projected on is an axis. I've looked at the word for fun, the word for work, and made that the axis of projection left to right. So you can see the most fun profession is evidently comedian. The least fun, I'm sorry to say, for the academics in the room is scholar. We also see engineers and physicians, and I guess being a bassist is not very fun. Engineers are good. Do you have one? Yeah, admin is fun, jazz is fun, just don't play. And I guess a diving bear is fun. Swimmer is fun too. Let's do the same profession, but let's project it another way. Let us project on an axis from the word for man on the left, the word for woman on the right. And now we get sort of a map of stereotypes that were in this data set, essentially. First of all, the men's names come up as clearly male. That seems reasonable. But I guess we've got drums and bass and baseball are all the super male professions. Whereas we have novelist, soprano, activist, that's interesting, chemist, so forth. had trained on that might have been hard to see before. All right. So this all lets you sort of get a sense of the training of the embedding itself. But how could you use this projector to actually see into what a network is doing?
So the use case and the mystery case we're going to talk about here is the notion of multilingual translations. So last year, okay, I'm going to go very fast. So last year, Google came out with this multilingual translation system where you input multiple languages and it knows how to translate out into multiple languages. And it was also a zero-shot system where sometimes it would bridge, here, I even have a visual. Sometimes it would bridge pairs of languages for which it had not seen training data. And the mystery is, how is it doing this? How is it resolving this space of multiple languages at the same time? So we talked to the researchers who were building these systems, and one of the fundamental questions they had, so this is one of the systems, you have an encoder on the left, you have a decoder on the right, and in the middle there you have the attention vector, it's called. And what we decided to do to try to solve this mystery was focus on the step between the encoding and the decoding. Basically a representation of the embedding space, okay? And the fundamental research question they had for us is, what does the multi-language embedding space look like? Does it look like the image on the left here, where you can imagine, oh, is the system, putting English on the top right and Portuguese on the top left and Spanish on the bottom right? Is the system dividing the embedding space into different languages? Or is the system doing more of what's here on the right? Where is the system sort of melding everything together? Are all these languages showing up together in the embedding space? And this is something they had no idea. And so basically what we did is we decided to use the embedding projector to start looking into this. So you might ask yourself, how did we go about doing this? We decided to visualize sentences. Instead of visualizing just a single word, they would give in sentences into these systems. For instance, the stratosphere extends from 10 kilometers to 50 kilometers in altitude. And then the system would have to translate into multiple languages, okay? This is what a sentence looks like in the embedding space. It's a bunch of dots, each dot is a word. So far so good, it's exactly what you guys were looking at before, right? One thing we did to the visualization, we added traces. So basically, this now is a single sentence. So far so good. The question is, when you have the same sentence in different languages, does the space of the sentences look like this, where I have English on the bottom left, and I have Portuguese at the top right? Or does it look like this, where they are co-occurring around the same space? And so what we found out after doing visualization is that indeed it's the second version. These things were showing up together. What you're looking at here on the left, this big overview visualization, is a set of hundreds of sentences that have been translated into multiple languages. What we're doing is we're coloring each sentence and its translations by the same color. I have three languages here. I have English, Japanese, and Korean. And so the fact that these same color dots, again, they're same color because they're the same sentence, not the same language. The fact that these things are clustering together tells me that the system is creating a single model for all the multiple languages. This tells me that it's basically the first sign of what we call interlingua. Okay, interlingua is a universal language. So what the system is doing, that's pretty incredible, is that it's coming up with a universal language. And so the way it resolves these multiple languages, it comes up with an even more high-level abstraction. And so when we look at that zoomed-in cluster there, that indeed is the stratosphere extends from 10 kilometers to 50 kilometers in all 3 languages. I can also show you the same cluster colored by these 3 languages and 3 sentences there. So the really exciting thing is that nobody had been able to generate a picture like this. And it was amazing to actually see how the system was thinking. The other thing the system showed us with this visualization was that when we looked at a different, also multilingual model, this one was for English, Portuguese, and Spanish, we saw a very different image. It's the image on the left there. And as you can see, there's a neighborhood that is all red, so it's a single language. Happens to be Portuguese to English, was all hanging out by itself. So unlike this image here, we had a completely separate neighborhood there. And when we looked at those translations, it turned out that those translations were bad quality. Okay? So what it told us is that the geometry of the space really matters, and that you could use the geometry to start debugging your system. Because if you end up with a multilingual system that has a neighborhood of a single pair of languages, that's probably a bad neighborhood. That's probably you want to debug out of your system. So this generated a paper, this was published. So hopefully this starts to give you a sense of how visualization can start to play a role in machine learning, all the way from scientific insights to explanations to different kinds of transparencies that might be useful.
We will conclude there. There's a lot of questions, I think, to be answered, and hopefully maybe some people in this room will be able to answer them. And our basic conclusion can be summed up by, yes, this is a fascinating area to work in. I think there's a lot of really interesting applications, and I would say this, come on in, the water's fine. Yes. Thank you very much.
Many thanks for the awesome talk. Really great. Looking at the 5 minutes questions. We have time for a few questions. Meanwhile, a little technical question. When I give an introductory talk about EuroVis, I always tell people never use 3D. Now I see all those rotating scatterers. Can you comment on that?
Yeah, great question about 3D. I think this was actually probably the first 3D visualization we worked on. And I think that it's definitely a mixed lesson, but what we found was for some of these TCD diagrams, it actually just made things better, easier to separate in 3D than 2D. That there was actually something intrinsic about the 3 dimensions that it gave you more space to operate in, it gave the algorithm more space to operate in.
Maybe, if I can. Sure. I'll try just like this. So, it was very nice to see your third presentation part, the one with projections. So, I've been working with many people here with projections for a while. There's something though that frightens/puzzles me in that area. Well, as you all know, the visual patterns that you see in projection might not be reflective of similarities, neighbors, patterns in the high-dimensional data, and that holds, unfortunately, for all the projections we know out there. So, how can you defend the extraction of feedback from something which can be between very accurate and completely inaccurate. I don't know the concept, but
yeah, we wrote an entire article about this for T-SNE. It's called How to Effectively Use T-SNE, and because of exactly what you said. Because it is so kind of easy to fool T-SNE in a sense. There are many specific ways of playing with the algorithm that really changes what the results are. So at the same time, it is one of the most useful high-dimensional projections that we know of. So I don't think there is a perfect answer, but at least having some notion of some of the trade-offs that you get when you use that technique, I think is really important.
Yeah, I would echo that all of these are just by their nature impossible. It's just like looking at the full 200-dimensional space. It's like looking at the face of God and you die or something. But we can get these glimpses. The other thing that I would say that is really important is that in a research context, these are all part of an analysis process. So in fact, to quickly go back to this slide here, you can see that on the left is a visualization, and then on the right is a statistical plot that we use to verify that what we saw was actually correct. And this is actually, when these things are part of the whole process, what you're saying, I think you see something and then you check it. So it's important to have a kind of trust but verify attitude towards high-dimensional visualizations.
I can shout. While I wait for the
Hi, Sam. Yeah, I really like your presentation. It was really interesting. But what keeps me a bit surprised is that you've been able to work with machine learning people. What I mean is, I'm not working with applications, real applications, but with academic. There seems to be pretty difficult. There are some difficulty working with academics because there are some different backgrounds. And is it because you're working at Google and we're trying to address practical problem where the academic issues don't go too much into play, or do you have any trick to tell us for working with machine learning? What I mean for that is most of the machine learning conferences are about assessing the quality of different machine learning algorithms without any human in the loop. So each time you talk about having a human in the loop anywhere, that are really frightened. Like, if we put a human in the loop, we're never going to publish anything because this is bad. And that's the discussion, the start of the discussion at the academic level. So what's your feedback on that?
So I think there's a couple of thoughts there. One is, yes, anytime you talk about applying machine learning in the real world, it's much more of just we're going to automate the heck out of everything. So even within Google, it's sort of like people need to trust what's happening with these systems and predictions to a certain level of trust, of transparency before they're willing to, launch something. So there's a lot of processes that go on about, yes, I can see that your system is performing well, your machine learning system is performing well, and now let's sit and try to understand together what does that mean, for instance, for my product, and how do I check that things are, are going to continue to go over well. I also think that there's a whole new area of machine learning that's becoming much hotter, where the human needs to be in the loop, and that is the whole notion of transparency, even from a legal perspective. Here in the EU, right, there are policies that are going to be in place by next summer. And so when you talk about transparency, algorithmic transparency, you're going to have to start thinking about the human in the loop very, very quickly.
I'm sorry, I think we have to stop now. So if you have more questions, please find them at the coffee break. Let's thank our speakers. And we will have coffee break right on the right.